So welcome everyone to the ArtIAMAS seminar series, which is co-organized by University of Maryland, Baltimore County, University of Maryland, College Park, and Army Research Lab. We are fortunate to have today's speaker, Dr. Shuvra Bhattacharyya, and the title of his talk is Embedded System Design Optimization at the Network Edge. Let me introduce Dr. Bhattacharyya. Dr. Bhattacharyya is a professor in the Department of Electrical and Computer Engineering at the University of Maryland, College Park. He holds a joint appointment in the University of Maryland Institute for Advanced Computer Science and is affiliated with the Maryland Crime Research and Innovation Center. He also holds a part-time visiting position as chair of Excellence in Design Methodologies and Tools at the National Institute for Applied Science in Rennes, France. His research interests include signal processing, embedded systems, electronic design automation, machine learning, wireless communication, and as well as wireless sensor networks. He received the PhD degree from the University of California at Berkeley. He has held industrial position as a researcher at the Hitachi America Semiconductor Research Lab and compiler developer at Koch and Associate. He is a fellow of the IEEE and a past recipient of the NSF Career Award. So thank you, Shuvra, for accepting our invite. So stage is yours whenever you are ready.
Okay, thank you very much, Nirmalya, for the introduction and also for the opportunity to present at this seminar. And so you can hear me okay?
Yes,
yeah. Okay, good. So yes, as Nirmalya mentioned, the title of my talk is Embedded System Design Automation at the Network Edge, where I'll be talking about some abstractions and design methods to raise the level of design abstraction as the systems are getting more and more complex. And I like to make an analogy to how we transitioned from assembly languages to what are now known as high-level languages several decades ago, where the complexity of the systems was getting, the complexity of of programming this processors was getting so complex in the lower level assembly language that we had to look towards higher levels to make it more manageable. And similarly, we have been in a trend now where the higher level language code is now exceeding hundreds of thousands to millions or tens of millions or even more lines of code in important kinds of applications, including many mission critical applications. And so it's to really be able to get the leverage the power of the existing hardware platforms and also develop applications with reasonable confidence and productivity, we need to look for higher levels of abstraction that go above the conventional types of programming methods. So that's sort of the center of my research at University of Maryland, and I'm really glad to be in the ArtIAMAS Center now, collaborating with researchers at ARL and also with my colleague Ben Regan at University of Nebraska in a couple of ArtIAMAS projects. So this is an outline of my talk where I will motivate data flow methods as a paradigm for establishing powerful abstractions that work in conjunction with conventional programming methods like using C++ or C or OpenCL, Verilog, VHDL. But data flow methods provide a higher level of abstraction that are effective for many kinds of signal and information processing applications, including the machine learning kind of applications and knowledge extraction from arbitrary kinds of sensors. So I'll give a motivation, and really the center of the talk is to motivate this concept of data flow methods. And then I'll give an example, a representative example of one class of data flow techniques that we have been developing in recent years, which are called data flow schedule graphs. And I'll present concretely some of these ideas with a real-time target classification system that we have actually been developing in some prior work with ARL. And then I will summarize. So some of the motivation for this area of work is the very complex kinds of constraints and challenges that we're working with in embedded sensing systems. And we're seeing a continuously growing variety of different kinds of sensors and lots of advances in sensing technologies, and also in communication techniques, machine learning to extract information from these devices. And so these are bringing up a wide range of applications in complex kinds of distributed sensor networks, with lots of diversity at many levels, like the platforms and the algorithms and the sensors, the design metrics themselves. And so this leads to a lot of complex trade-offs that must be managed to be able to leverage these kinds of technologies closer to their full potential. And also to be able to reasonably deploy applications in a reasonable amount of time. And if we're not able to do that, if we're not able to deploy these applications productively, we have to fall back to older technologies that we have more confidence in. So there's a lot of cost in terms of what we're able to use. And so the goal is to help, the goal of this kind of research in model-based design methodologies and embedded software systems is to help bridge that gap between the capabilities offered by the latest algorithms and hardware technologies and those that are actually, that we're able to deliver through practical engineering efforts. And so the central problem that we address in my research group is something we refer to as the implementation gap, which is illustrated on the right side here, where we're seeing more and more complicated applications that are emerging with advances in technology or and advances in algorithms. And sometimes, in many cases, the advances in the hardware actually drive new advances in algorithms. And I think deep learning is an example of that, where suddenly a whole enormous class of algorithms became feasible at a certain point, when it became possible to train these networks to perform at a sufficient level of accuracy. And so we're seeing more and more complex applications that are driving us to more and more complex systems at one end, and at the other end, we're seeing more and more complex hardware platforms encompassing larger numbers of devices, millions of transistors now on these devices, and also large amounts of heterogeneity. And so you can view this as kind of a growing implementation gap between the complexity of the applications and ultimately the low-level platforms onto which we have to map those onto to deploy those applications. And so the goal of research in my group is to help manage this implementation gap so that we can leverage these existing technologies more effectively in the context of modern applications. And so this is kind of an illustration of what we're, the general methodologies that we pursue in my research group, which is, on one hand, we look at domain-specific ways of working with different types of signal and information processing algorithms. And we're interested in all sorts of signal processing and extracting information from all sorts of signals, and also combinations of signals in various kinds of multimodal systems. And what we try to do is to capture the application structure at a higher level of abstraction above, but interoperable with these conventional languages that that engineers are working with, that are closer to the platforms like C and C++, Verilog, VHDL, and many more that I listed before. But we like to explore abstractions on top of those that capture the signal flow structure, but not just in sort of a cartoon or informal flow graph form, but in a way that precisely captures the computation and communication going on at the higher level. And then we wish to explore analysis and transformations to help transform these efficiently onto different types of hardware platforms or heterogeneous combinations of these platforms. So we refer to my research group as the DSP CAD group, which stands in kind of reverse order for computer-aided design for digital signal processing. And so actually the data flow technology has been evolving now for several decades. It actually started with some work in France in the late 1960s with the theoretical underpinnings of data flow that are still extremely important, and also in work in computer architecture that was based on pioneering data flow techniques developed at MIT. But the kind of data flow we use is kind of different from those original architecture-oriented techniques in that the data flow in my research group that we explore is using data flow more as a programming model and as a model for analyzing applications as opposed to as a form for computer architecture. Instead, we use it as a way to represent applications so that we can more efficiently explore the design space when mapping onto different types of hardware platforms. And so data flow as a programming model has also been evolving for some time. It got a lot of boost in the 1990s from various kinds of tools in the wireless communication area where data flow is an especially strong match. And these are some representative commercial tools. GNU Radio might not be technically a commercial tool, but it's used in many commercial settings. And then there's Agilent and LabVIEW, which are all pioneers in terms of commercial data flow technology. And since then, as this complexity of systems has been increasing, we've seen a move to, even though it's uncomfortable to and disrupting to go to new kinds of programming models, there has been more and more acceptance of this in different application areas. More recently, in the machine learning area space, we see tools that have genuine data flow semantics like TensorFlow, for example. So this is kind of a brief overview on what I mean by data flow and the form of data flow that I'm referring to, which is where applications are represented as directed graphs, where the vertices of the graphs represent computational modules. And these computational modules can be of arbitrary complexity, which gives rise to some of the flexibility of these data flow environments. So the edges represent first in, first out communication buffers, which you can view as passing signals from one computation to another, or streams of data samples. So, and this is all a very sort of mathematical or abstract kind of representation without any particular implementation in mind. So, for example, what we see below here is an example of a simple data flow graph with three actors, X, Y, and Z, which represent three computations. The X might be some interface to the outside world, like to a to D converter or something that's reading data from a file. Similarly, the Z could be an interface on the other end, like a interface to a D to A converter, and Y represents some processing going on in the middle. And so these X, Y, and Z you can view as sort of being modules that encapsulate some code in some arbitrary language, like the ones I've described before, C++ and C, C++, and so on. And the edges are passing data. These computations produce and consume data as they execute, and the data is passed along these edges, and we refer to each data value as it's passed as a token. So a lot of the analysis in data flow graphs doesn't care about the data values, but rather at the rates at which they're being produced and consumed, and the overall graph structure of how these modules are connected and how they communicate. And so this idea of production and consumption of these modules is actually a very a key aspect of these data flow models. And so these P and C annotations on the edges here, or on the ports connecting the actors to the edges, represent what we call the production and consumption rates. And in the most general form, the production and consumption rates can just vary arbitrarily as these actors execute. So P1, I here means that X is producing some amount of data on its ith execution. onto the edge E1. So P1 comma I represents that quantity of the number of tokens produced on the ith execution of X. Similarly, C1 comma I represents the number of the tokens or the amount of data consumed by actor Y from edge 1 on the ith execution of Y. And so that's sort of the most general form, but often in many kinds of, for many practical actors, we have a lot of information about the production and consumption rates. For example, in many cases, they may be constant. So P2 comma 1, for example, might just be a constant value 5 for a given actor Y. Or if they're not constant, they may be cyclically varying, or they may be varying in a very controlled way based on some data tokens elsewhere in the network. So one of the things we want to do when we analyze these data flow graphs is to characterize these production and consumption rates as precisely and as specifically as we can, and that leads to different kinds of high-level analysis that we can apply on these graphs to help optimize the systems and also to help prove certain kinds of properties like bounded memory or deadlock-free execution. And so at the essence of that is representing these applications as directed graphs and also characterizing the production and consumption rates of the different modules in the system. So one of the key things that we have to do when we implement a data flow graph is what we refer to as scheduling the graph. And this is actually the need for this arises because of a very important property of data flow, which is that it separates the ordering of the computations from the actual behavior of the application. So this is very different, for example, from a C program where you write a bunch of functions, but not only do you specify what those functions do and how they are producing and consuming data or transforming data, but you're also specifying, you also need to specify the order, like through loops and if then else statements and so on. You're also specifying the order in which these are going to execute in your program. But data flow untangles that. The representation I showed you before is just showing how modules communicate data with one another in the underlying algorithms that are applied. But the actual task of ordering those so that they execute on a particular platform is left as an implementation issue. It's not tangled up in the basic data flow representation. So this concept of actually decoupling important design phases has an important term in software engineering and also in design automation. In software engineering, we call this separation of concerns. And in design automation, we often refer to it as orthogonalization. So this is a really fundamental form of separation of concerns in data flow, which is that the scheduling is separated from the application behavior. So this allows us to keep the application behavior fixed and experiment very flexibly with different kinds of schedules without having to go back and tweak our representation of the behavior. So scheduling in this context refers to the assignment of application tasks or the vertices in the data flow graph to different processing resources that are available, like different processor cores or GPUs or FPGA subsystems. And it's also talking about the relative ordering of tasks that are a time multiplexed onto the same resource. Like a given processor core may be only executing a given actor at a single time. So the scheduling part of the design process has to specify how are those actors sharing going to be coordinated on that individual processor core. And scheduling has very big impact on key implementation concerns. Such as the latency or the response time and the throughput, the memory requirements, and also energy, power, and thermal considerations as well. So it has very big impact on all of these, and often there are very complex trade-offs involved. And so having a more formal and a higher level and more structured approach to scheduling can be really effective in exploring these complex design spaces and trade-offs associated with metrics like this, so that we can gear our designs towards a strategic combination of the trade-offs rather than just relying on some default set of priorities that a prepackaged tool has given to these trade-offs. So one of the things that we do when that we have the opportunity to do when we do scheduling of data flow graphs is to reason about different forms of parallelism, which is very important because parallelism is a huge theme in modern hardware platforms, where we're in the many core era, many cores integrated onto single system on chip devices, as well as combinations of GPU subsystems and CPU cores and FPGA units and so on. So data flow gives us a very structured way to reason about different types of parallelism. For example, we can talk about task parallelism, which is where different actors execute at the same time on different hardware. So here's a simple data flow graph where there's some inherent concurrency between the processing between B and C before the data produced by them is consumed by D. So here we can, in this kind of a schedule, if the horizontal axis represents time, we can see that B and C are being executed at the same time in parallel, and then the results are combined in D and so on. So there's task parallelism here because we have two different actors, B and C, executing at the same time. So there's other kinds of parallelism that can be used. There's, for example, pipeline parallelism, where we can have overlapping execution of different data flow graph iterations. This is also referred to as software pipelining in the compiler terminology. And so here, because these are processing, these data flow graphs are often processing these semi-infinite data streams coming from some continuous stream of data from various sensors, you can view the graph as just executing over and over again. So there's one iteration after the other executing of the graph. So in pipeline parallelism, we can overlap these successive iterations of the graph. And so here we see that processor one it starts, and then after this transient phase where the first execution, the first iteration of A and B execute, then the second iteration of A and B executes in parallel with the first iteration of C and D. And then this can continue where iteration C and D from the previous iteration of the graph is executing concurrently with A and B from the current iteration of the graph. And then we can also talk about data parallelism, which also has a very concise and easy to understand description in a data flow context, which is that different firings of the same actor execute at the same time on different hardware. This is actually the same kind of parallelism that GPUs are optimized for, but GPUs do this at a lower level of abstraction. And so this becomes a complementary representation to GPUs as well. So here, different firings of the same actor execute at the same time on different hardware. So another way we can execute this graph is to execute start the first two iterations of the graph at the same time by executing two invocations of A together, and then the data for the first two invocations of B will be ready after that, so we can execute two executions of B in parallel. So data flow representations allow us to reason about these different forms of parallelism, which is complementary to the emphasis on platform-based tools like with the CUDA compilers and C compilers and hardware synthesis tools that focus on what's going on in individual blocks of code in these different conventional languages. So they're very effective at optimizing the code inside these modules, but they're very limited, or they don't make use of these formal data flow representations at higher levels of abstraction. So we have a lot of opportunity to explore complementary kinds of optimizations and analysis to what's going on at the lower levels. A lot of the lower level optimization for the platforms is oriented towards specific kernels, like accelerating a fast Fourier transform or a digital filter or a machine specialized kernel inside a machine learning algorithm. The platform's benchmarks are often cast in terms of these very critical low-level kernels. But there's a lot of other application code outside of those, and the data flow representation helps to capture and integrate all of those while having a back-end path, because ultimately in this design process, we're going to go through those kernel-oriented tools as well. So we have an opportunity to do all this complementary analysis on top of conventional lower level optimizations. And also this data flow research over the years ends up influencing these more powerful tools, like, or these more platform oriented tools, or the lower level tools. A good example is TensorFlow, which has been influenced by previous years of data flow research, and also those communication-oriented tools that I illustrated. They also drew a lot from the data flow research, and I've had collaborations with all of those groups as well, the GNU Radio and National Instruments and Agilent Technologies. And so there's definitely not decoupled, but there's a general emphasis in the platform-oriented tools to have as a first priority sort of extracting the lower level features of those platforms and making those available, whereas in the goal of model-based design and data flow oriented research is to capture the high level structure of applications and manage the complexity of these ever increasing of these ever growing complexity of applications. So I gave some motivation for data flow methods, which again is sort of the core part of this presentation. And let me now go into detail to show in some more concrete detail some of the kind of things we can do with data flow graphs, especially as they apply to scheduling, which is a very important problem, as I motivated before, because it dictates how efficiently, in many ways, that we can use the different types of platforms that we have available to us. So we've been developing a representation in my research group for the past several years called the data flow schedule graph, which takes the formal behavior of the application that's given by the data flow representation and develops another data flow based representation, but this data flow representation captures schedules in a formal way. So the conventional way is to take the data flow behavior represented as a data flow graph and then implement the schedule using whatever platform oriented language you're using. And you can still get a lot of advantages of data flow by doing that, because you're starting with a formal data flow representation and the schedule has a separation of concerns from the application. But data flow schedule graphs go a step beyond that by making a formal representation of the schedule. So as schedules get more complex and we're dealing with more and more types of processors and a larger number of processors, we can use these graph-based techniques and data flow principles to reason about properties of the schedule and also transform them to derive more efficient schedules. So the formal schedule representation of data flow graphs provides a higher level of abstraction for the design, analysis, and optimization of these schedules, as well as correct by construction development of schedules where certain properties of the schedules are guaranteed as a byproduct of the design rules that are used in the formalism to represent the schedules. Again, a big contrast from C, where it's a very general purpose representation, which is nice because we can represent all sorts of different types of schedules and functionality. But because of this generality, we don't get much in terms of formal guarantees about key properties of the schedule. Like key examples that are important in processing these huge volumes of sensor data are things like the bounded memory and the avoiding deadlock as the system continues to execute, and also in ensuring the determinacy so that we don't encounter race conditions when different resources are contending, different tasks are contending for different computational and communication resources. So A DSG data flow schedule graph is a data flow graph that represents the time multiplexed execution of a data flow application or subsystem on a given resource. So, and also it's very broad because you can use different types of actors in the DSG to represent different ways you want to coordinate execution within the schedule. And so a broad class of schedules can be represented with these DSGs, a very large class, and the actors in DSGs can dynamically control the flow of execution. So we still have a very general format, but it's also very structured. You can't just write any arbitrary types of control in any arbitrary style. It needs to be built up using data flow actors to represent the schedule. So DSGs provide a formal abstract representation for data flow schedules. And these are platform and language independent, so they can allow us to represent and reason about schedules at a level without yet committing to a particular implementation. And so there's been a lot of work in the evolution of different types of modules for scheduling in different types of data flow research. And I won't go into these details here, but I'm glad if anybody wants to follow up later, I'm glad to discuss more in details and provide references. But let me just summarize that compared to the related work in this area in terms of model-based schedule representations, the DSG goes beyond the previously developed techniques, which were largely focused on representing very statically structured schedules. So those are schedules that actually work for those types of data flow graphs where the production and consumption rates are completely constant, which is one example I gave of a very predictable kind of production and consumption behavior in data flow graphs. But in general, now with complex applications, we often need some amount of dynamics in the graph and also in the schedules. And so the DSG goes beyond these and provides this kind of dynamics. So here's an example of a DSG. So we have, again, a very simple example to help to concisely illustrate the points. So here we have another very simple example of a data flow graph, maybe acquiring data from a sensor, doing some processing with B, maybe some filtering, and then sending the data to the outside world or to a file. So this is what we call the application graph. When we use the DSG methodology, we now have two graphs that we're working with. We have the original data flow graph, which is the representation, the behavioral representation, which we refer to as the application graph. And then we have a schedule. Whatever schedule we want to work with, we have a data flow representation for that, which is what we call the schedule graph. So a given application graph can in general have many different data flow schedule graphs that will achieve the same functionality, but they may have very different trade-offs in terms of the different metrics that we're interested in. So here's an example of one DSG for this schedule. So for this data flow graph, this DSG represents a schedule where you can view this sort of as an outer infinite loop. That's what this infinity represents. So this is, you can view this as the system is just receiving data continuously from a bunch of sensors until the system is turned off or runs out of batteries or somehow terminates due to some asynchronous event. So there's this outer loop of all the iterations of the data flow graph. And then because of this production and consumption rate mismatch, there's 2 tokens produced for every 1 token consumed by A. So B needs to execute twice for every execution of A. So we execute B twice in a row in this schedule. That's what this 2B represents. So we execute A and then 2 iterations of B, and then we execute C to consume the 2 tokens that were produced by B. And then this A, 2B, and C, this just keeps iterating over and over again. So that's the intuitive idea of the schedule. You can envision implementing that in C very easily by throwing a call to the function for A, and then a simple loop of 2 iterations for B, and then a call to the function for C. But we can represent this formally as a data flow graph. And of course, for something so simple, it's not obvious why this would be of any use. But this is to illustrate, just to illustrate this so you can get the idea concretely. If you can imagine this being applied now to schedules that encompass hundreds of thousands or millions of lines of code, and then you can see how having the formal representation would be useful. But here what we have is a loop representation of this infinite loop, but it's represented as a pure data flow actor that operates under data flow semantics. And then we have these other special actors called R, A, R, B, and RC. Those are referred to as reference actors. A reference actor you can just view as having a pointer to an actual actor in the application graph. So it's a reference from the schedule graph to an actor in the application graph, and it just executes the application graph that it's referenced, that is referenced. So the DSG represents 2 main types of actors. There's this schedule control actors like the loop and actors, which are sort of coordinating the flow of execution in the schedule graph. And then there are the reference actors, which are telling us when to fire specific actors in the application graph. So I'm going to go through some of these details up here. There are many tests. So one thing is a general methodology. So we have a lot of, we have really arbitrary flexibility for implementing these schedule control actors. We can have many different types of these schedule control actors and make them very application specific in some cases, with the only thing being that at their interfaces they have to satisfy certain data flow design rules, which have to do with the fact that they produce and they have to be formulated in terms of producing and consuming data from their input edges. And they cannot just have arbitrary side effects in other parts of the graph. So this is also related to what's called a functional programming style. So as long as we adhere to that functional data flow programming discipline, we have a lot of flexibility to build up these different types of schedule control actors. And this is how we get this flexibility to implement lots of different types of schedulers to control complex applications in many different ways. And so the whole scheduling methodology wouldn't be useful for modern platforms if we couldn't represent parallel schedules. And so this data flow graphs, data flow schedule graphs have a natural extension to what are called concurrent data flow graphs. What I've been talking about so far, like the example I showed you before with the A, 2, B, and C, that's what we call a sequential data flow schedule graph. You can think of that as specifying a single thread of execution. But we can have an arbitrary number of these sequential data flow graphs representing what's going on the different threads of a platform or a class of platforms that we want to target. And then we introduce one additional type of schedule control actor, which is called an inter DSG coordination actor, which represents the communication between the between SDSGs. So concurrent schedule data flow schedule graphs are composed of multiple sequential DSGs. Each of the SDSGs provides a subschedule associated with a different processing resource or a different thread in a multi-threaded type of lower level representation. So this is nice because threads are well known. Threads are they're very powerful, like programming languages like C and C++ in terms of their generality, but they're also very error prone and very difficult to get very high in complex systems to get very high reliability, high predictability implementations with a reasonable amount of design effort. And they're also very hard to retarget as the platform changes. So we're using, again, the same lower level technology that platforms are optimized for, which, again, are thread-based implementations, but providing this abstraction on top of them so that the threads are, the functionality of each thread is represented in a formal way. And SDSGs, as I was referring to a little while ago, SDSGs on different processors communicate using a third type of DSG actor that we call an inter-SDSG coordination actor, ISCA. So previously I talked about reference actors, which refer to application graph actors, and about schedule control actors, which are directing the flow of control inside a given thread. And then there is this third type of actor, which is representing the communication between the SDSGs. And again, that's an abstract representation which can be targeted to different types of communication fabrics and communication mechanisms. So CDSGs provide a model-based representation for parallel, multi-core, and heterogeneous schedules. There's no restriction here in anything I discussed about using a certain type of processor or using the same type of processor. It's just talking about how we partition the graph into different threads and how we're coordinating the execution on the threads and how their threads are communicating. So let me skip through a few of these. We have developed a software synthesis tool in my Dataflow, in my research group. And this is sort of an illustration of what the design process looks like. Here's what on the left side is what the designer provides. The designer provides two graphs now, and these are specified as data flow graphs. So they specify the application as a data flow graph. And we have a language that we've been developing in my research group for many years called the Dataflow interchange format package, which is a lightweight language that's designed to just specify the data flow structure of an application. And then it has ways you can link that to arbitrary libraries that implement the individual actors in different languages. So, but instead of just specifying the application graph as a data flow graph, the designer will also specify the schedule as a data flow graph. And the schedule could also be output by some other data flow tool. The DSG can also provide an intermediate representation for scheduling, automated scheduling tools as well. So then these two graphs are then parsed by the diff package, which is our software synthesis tool, and then linked with various libraries. And the diff package basically iterates through the structure of the DSG and generates some streamlined runtime code that actually interprets the DSG at runtime. And the mapping of the SDSGs to the target platform is conventionally very easy because the separation into threads has already been done. It's a matter of translating the structure of the code into whatever language you're using in the target platform and the communication library you're using. So the model-based synthesis process can readily be retargeted to generate code in other languages. And as a case study, we have a real-time classification system that we've been experimenting with among different applications. This is actually something that evolved from our earlier work several years ago with a scientist named Raju Damarla at ARL, who is now retired, but I really appreciate the collaboration that started with his work and then continued with Benjamin Riggin and other ARL researchers. And this provided a really interesting application, both in terms of interesting multimodal sensor processing requirements. In this case, the idea was to use very lightweight and cheap processors, like disposable types of sensor platforms, to process data with very real-time detection of people and vehicles from seismic and acoustic sensors. And so this is using a novel algorithm that my collaborator Benjamin Riggin designed, which has to do with a technique called a cumulative feature concatenation, where cepstral analysis is used to extract features from the acoustic and seismic windows of data streams from the acoustic and seismic sensor streams. And then these are passed to some classifier. You can use actually any type of classifier in this framework. We use an SVM bank, a bank of SVMs to represent this. And then there's various post-processing to do a multi-class decision based on the scores, the classification scores. So this is for, again, multimodal classification using seismic and acoustic sensor streams to detect people and vehicles. So this is the data flow representation of the algorithm, like most actually signal and information processing algorithms we work with. They map very naturally into data flow representations once one sort of learns about the design rules and gets comfortable with the design rules of data flow representations. So you can represent this naturally as a data flow graph. So that becomes the application graph. These parameters represent the production and consumption rate. So there are some parameters in the systems like F and D and W. I think this is related to the window size. And the production and consumption rates are of the different actors are parameterized in terms of those parameters. So this is an example of a sequential data flow schedule graph that to implement this on a single thread. It has various loop schedule control actors and all these reference actors that then refer to specific firings or refer to specific application graph modules when it's time to execute them according to the schedule. But that's just one possible schedule. Again, as the number of possible valid or functionally correct schedules for a given data flow graph in generally can grow exponentially with the size of the data flow graph, which is, again, further motivation for why we want these formal techniques to be able to reason at a higher level of abstraction. So here's another, in addition to that single threaded implementation, here is a concurrent schedule DSG using 2 threads. So now we have broken it up into 2 SDSGs, and then there's these special ISCAs, which are inter-SDSG coordination actors. There's a send actor here, which is representing the sending of data to the other thread, and a receive actor, which is representing the receiving of data. Those are also integrated into the SDSG representations on those individual threads. So now we have the concurrent DSG representation where some of the edges are representing the communication between the threads. And here's scaling this up to a 3-thread representation. Again, the same principles where you have the schedule control actors, reference actors like these 3 lower actors here executing in a loop, and then the dashed edges are representing the communication between the inter-SDSG coordination actors. So just to give you some ideas of experimental results, we did some evaluation. Again, the goal was to use a very low-cost platform in our experimentation with this based on some requirements that were given to us by Dr. Damarla, who started this exploration with us some years back. We used a Raspberry Pi device with 4 CPU cores. It has a GPU, but we didn't use the GPU in these experiments. And here's an example of some performance evaluation results that give some insight about what's going on and some of the trade-offs. So there are sort of 4 sets of results here. There's a handwritten set of results, which is a hand optimized schedule that's written by somebody without using any concept of DSGs at all. You can view that as sort of analogous to somebody writing an assembly code implementation of an algorithm versus something being compared to a C-based implementation. So this is the handwritten implementation. It takes a long time to write and doesn't have the kind of formal properties and structure that we have with DSGs, but it achieves the best performance if you look at these results. And then you have DSGs using different types of DSG interpreters. So part of this research, initial research in DSGs involved different ways to have an efficient runtime interpreter for the DSGs, which is something you have to do. It's like a just-in-time execution subsystem for the DSGs. So there are various types that we explored, with the most advanced being the DTT variant that's shown here. So you can look at that, and we can see that as we move from the sequential implementation to 2 and 3 threads, we get reasonable speed ups, similar speed ups to what we see percentage-wise by the handwritten implementation, but the numbers are a little bit slower, just a little bit slower. And you can view this again as a modest performance cost that is seen in raising the level of abstraction and productivity and confidence in the schedule implementation. But you get a lot of useful properties. And again, you can see that the cost is not that high, because you can do a lot of things to use this formal structure to optimize the operation of it. Also the lines of code, you can see the blue is the with our synthesis tool, it's the code to maintain the schedule versus the handwritten schedule code. And so you can see it's a lot more compact. And so this code is compact to develop and maintain, in addition to the formal properties which give us certain kinds of guarantees associated with them that we don't have with the handwritten implementation. So this is very useful because scheduling code is particularly tricky, and with DSGs, the amount of that code that we have to maintain and write is much lower. So in summary, I've been talking about the novel constraints and challenges for embedded sensing systems and how this necessitates disruptive approaches to how we view the design process. We can't be, I mean, we have some constraints. It's just not practical to redo all of the work that's been done on conventional languages. There's a lot of powerful technology on C compilers, C++ compilers, hardware synthesis tools. We're building levels of abstraction on top of those, and we've discussed Dataflow as a core modeling paradigm for this kind of model-based design and implementation of embedded sensing systems. And this kind of methodology applies formal models and methods for high confidence system design, design optimization, and trade-off exploration. And some references at the end. So that concludes my talk, and I thank you all for your attention, and I would be glad to answer questions, and also offline as well after the talk ends.
Thank you. Thank you, Dr. Bhattacharya, for the excellent talk and enlightening us on the data flow graph. Excellent work. So any questions from the audience?
Yeah, I can ask one. This is Jianwu Wang from UMBC.
Yes.
Thanks for the talk. I'm familiar with Dataflow. This DSG is quite new to me. Thanks for explaining it. My question is, it looks DSG with one simple with one data flow graph. You can have multiple data flow schedule graph. Right? With multiple DSG, you can generate it by sequential and parallel. My question is, does the user has to provide this DSG manually? There's a scheduling optimization can generate this DSG automatically with some goal. You want a parallel, you want a sequential. Is that possible?
Yes, so that's an excellent question. And the goal, so this is sort of an orthogonal problem to the scheduling problem, which what you described as an extremely important problem is actually how do we construct these efficient schedules? And there's been actually the field of scheduling theory for these data flow and data flow-like representations is very rich and has lots and lots of different types of algorithms, but a lot of it is at a very abstract level. So the data flow graph helps to provide a concrete intermediate representation where you can apply those kinds of automated scheduling techniques and develop software for those, and then output those in the form of a data flow schedule graph, and then have code generated from those. So you can, when applying some automated scheduling technique, you can view that as like an intermediate representation. And actually, there's a lot of the other research in my group has to do with different types of scheduling problems. So it's a very, very important area. But another thing is that data flow schedule graphs opens up this possibility of design, making it easier for designers themselves to work on these schedules. And designers often have a lot of insight into what could be a good schedule, and you know, sometimes that can be very difficult to mimic with or to achieve with a fully general automated algorithm. So the Dataflow schedule graph also makes it more possible for the designer to apply their unique insight for mapping a particular application to a particular platform.
Yeah, thanks. Yeah, to me, this DSG is a middle layer between the actual implementation and the high-level data flow graph with this separate another layer abstraction. You have different ways to optimize it, and also different like property enforcement, those kind of things you can do. Thanks a lot.
Yes.
Thank you, Giano. Any other questions? We have a few more minutes to take one or two more questions. So, Dr. Bhattacharya, I have a quick question. So,
Yes.
as you know, in the ArtIAMAS, one of the focus is robotics. So, I am just thinking, have you seen any work, or are you familiar with any work of application of data flow schedule graph in a robotics area? Like, consider you have multiple aerial system, multiple ground vehicles, and how they can effectively communicate with each other. And I see your approach could help us to enhance this communication. And from the communication perspective, from scheduling perspective, what's your thought on that?
Yeah, that's a very interesting question. And I think the road through impacting the control area goes through MATLAB in some sense, which has been a difficulty because MATLAB has a lot of use in the design of or validation of different types of control algorithms, but it's inherently not a data flow based tool. They may have been exploring some data flow techniques. So that's one practical constraint that there has been in terms of just getting data flow integrated into standard design processes. Whereas if you see like the path from communication tools to data flow implementations, there's more examples of that. So some of that is based on the practical tools used in the area. There is an area of work. I've worked with a collaborator, Bill Levine, who's an expert in control. And we argued that a control system, actually, once you've designed the control parameters, it's a signal processing system. And you can represent it very well using data flow graphs. So I think there's a lot of synergy there. But it just hasn't been connected in terms of a complete design flow that works. I think there's a lot of researchers working on different pieces of it, like using different types of control systems as benchmarks to drive their data flow research. But there isn't really this end-to-end kind of tool flow yet.
Thank you.
I think there's a lot of opportunity in that area. So it's something that I'm also interested in exploring as part of ArtIAMAS.
Thank you. Thank you. Any other questions from anyone? We are just on time. Okay, if not, let us thank Dr. Bhattacharya again. Thank you, Dr. Bhattacharya, for your excellent talk.
Thank you very much.
Thank you. Thanks, Shuvra.
Thank you. I think that's all. Thank you.
Okay. Have a nice day.
Okay, bye.